Welcome to the lesson on special right triangles. I did want to let you all know that we will not be in the habit of doing more than one lesson in a day. It just so happens that special right triangles is an honors topic, so we wanted to go ahead and give you both lessons so that you can be on pace with on-level geometry students for the rest of distance learning. But that will not be a common occurrence that you have the two lessons. Once we get going in distance learning, we'll actually have a slower pace than normal, so I think you guys will find that it is a little more leisurely. And nice, as we have some new and pretty different topics coming up in this chapter. If you have not already watched Ms. Beasley's video over Pythagorean theorem, I do want you to go back and watch that one first. I know that most of you are confident with Pythagorean theorem, but it does have new information about how to tell if a triangle is right, acute, or obtuse, and you're gonna want that new information. So if you haven't watched the Pythagorean theorem video, do that first, come back to me. For those of you that have watched her video, you're ready to go with special right triangles. So before we get started with the content, I do want you to get out a piece of paper and something to write with. Treat this like you're taking notes in class. I know that learning from a video might be a little bit more boring at times, so you're going to need to have that writing piece of this to keep yourself engaged, try to keep yourself focused on what we're doing here, just like you were in class. So if you haven't gotten a piece of paper, writing utensil, pause the video, get that first. Okay, so once you've got your stuff, it's all in hand, you don't need a calculator today. For today's lesson, we're gonna do some mental math here. But before we get to our special right triangles, and they are very special, before we get to that, I'm gonna add in one concept about simplifying radicals. I know that Miss Beasley went over just the basic simplifying radicals, like what happens when you're doing Pythagorean theorem, but there's another thing that happens with radicals when they're in the denominator that I also want you to be comfortable with once we get into the special right triangle solving, because it happens quite a bit there. Okay, so simplifying radicals when we have a radical in the denominator. Go ahead and write down example 1. We've got the 7 over radical 3. And the issue here is that we're actually not allowed to have a radical in the denominator of an answer. Or typically we don't want it in this form. So the way that we get rid of that radical 3 is that whatever that denominator is, we're going to multiply the top and the bottom by that. So in this case, I'm going to multiply the top and the bottom of this by radical 3. And because I'm multiplying by radical 3 over radical 3, it's like I'm multiplying by 1. So I'm allowed to do this. I'm allowed to multiply anything by 1, and I'm going to still not change that 7 over radical 3 as far as the value of it. So when I multiply my 7 and my radical 3, I'm going to get that 7 radical 3. But in the denominator, when I multiply a radical and a radical, I'm going to multiply what's inside of the radicals. So my 3 times 3, I get a radical 9. And because I multiplied by that same number, I'm always going to end up with a perfect square here, because we know that the square root of 9 is just 3. So anytime I have this radical 3 times radical 3, it's really like 3 squared, square rooted, which is always going to end up being itself. So this would be my simplified version of the 7 radical 3. It is 7 radical 3 over 3. And as long as we don't have a radical in the denominator, we're good there. If we could simplify the 7 and the 3 like a normal fraction, we would. So that's actually going to happen in our second example. Go ahead and write down this 8 over radical 2. So in this case, we always want to ask ourselves, what am I multiplying by in order to get rid of that radical? In that last one, we multiplied by radical 3 over radical 3 because that was the denominator. In this case, we've got that radical 2, so I'm going to be multiplying by my radical 2 over radical 2. So in the numerator, similar thing, I've got my 8 radical 2. In the denominator, my radical 2 times radical 2 is that radical 4, multiplying by what's multiplying the 2 and the 2 that are underneath the radical. And then just like on the last one, we're going to end up with a 2 in the denominator as we take the square root of 4. The only difference with this one is that we actually can simplify this one. I want to just notice that that 8 over 2, if it was just the fraction 8 over 2, we could simplify that. We could go ahead and divide 8 divided by 2. So you can think of dividing both of them by 2, or just dividing 2 into 8 is fine as well. It's important that the radical in this is not involved. It's kind of like a variable here, like if you had 8x over 2, we would simplify the 8 and the 2, the x would just stay x. So in this case, we're going to divide 8 divided by 2, and so that's going to be our 4, but we're still going to be left with the radical 2. And that would be our simplifying in this case. There's both examples if you need to see them both together. Now we're ready for special right triangles, and as the title suggests, they are right triangles that are special. So they're a very specific type of right triangle. If you recall from quadrilaterals, this is kind of like the square, because we started with the parallelogram and it had its own attributes, but then with the rectangle it had all angles congruent, the rhombus had all sides congruent, but they were still parallelograms, and then they gave birth to the square that had all sides congruent, all angles congruent, the little square perfect in every way. And as we say in my class, that the square was very arrogant because of this. It led to a lot of trouble in his life. The special right triangle is very similar because they're a specific type of right triangle. So not only are they right triangles, which is already really neat, but they are special. I like to think that these guys are not arrogant though, that they've overcome maybe just their natural athletic ability that they've got going on. They're very humble in what God has given them. That's what I like to think about the special right triangles. And when we're looking at these, we've got the 45, 45, 90, and then the 30, 60, 90. Those are our two special right triangles. We name them that way because we're talking about the angles. So when we say 45, 45, 90, we're saying that it has a 45 degree, and then that right angle, the 90 degree angle. Similar with this guy, it's got its 30 degree angle, a 60 degree, and a 90 degree angle as well. So what's neat about these guys, the reason that they are special, is the fact that normally with Pythagorean theorem, we can solve for a side in a right triangle as long as we have two sides already. The difference with the special right triangles is that we only need one side to solve for the other two, which is pretty special.